that you're able to, the new words, the new verbs that you're getting in this BQL language. But there's a bit more here. So let's make sure we have a good frame for all of it. So BayesDB comes with this BayesDB query language, BQL, which gets you model independent queries. And so that means, most importantly, like SQL got you queries that were independent to the physical structure of your data, BQL is going to get you a query that's independent of the underlying modeling technology. If you want to use a random forest or a k-means or naive Bayes, if you want to use the default model that's built into BayesDB, if you want to compose multiple models together, if you want to use Stan, if you want to use Venture, if you want to use the next shiny amazing object that helps you model data, the BQL query doesn't have to change. And this is about introducing that abstraction barrier that allows optimization of modeling to happen separately from the elicitation and enumeration of questions. So that's interesting because once we've defined that vocabulary of what questions make sense, it now becomes pretty straightforward for people to ask a lot more questions. And there's a problem with data science today. Answering each question in data science is actually very expensive. When I talk to people about this, I often ask, sort of business stakeholders, domain experts, like, what are all the questions you want to know about salespeople in fixed income securities? What are all the questions you'd want to know about your customers? What are all the questions you'd want to know about countries in Africa? What are all the questions you'd want to know about nutritional interventions? And people are really reluctant to give you a long list of questions. If you sit somebody down with an expert, they're happy to just ask that person question and question and question. But data science has taught people that questions are expensive, that it takes a week or 2 weeks. I need to go prepare a data set, staff a project, get something going. And so I need to be very careful before I ask a question. This is a big thing we want to change, disrupt, if you like those words. We want to say that, no, you should be able to ask lots of questions. You should be able to be skeptical of your model. In order to do that, we need the ability to build models that can answer any question you can say in BQL. And so we also have an automatic model builder, or what we call a machine-assisted model builder. So under the covers in BayesDB, we can automatically model your data and then be able to answer any question you want. So that's good. That lets you start to explore what's going on. And then we can also compose in models. And this is actually really important. Most data science suffers, most statistics suffers not only from being about broad generalizations and relatively expensive to do, but it also suffers from the fact that you can't combine two models. There's 1 + 1 is type error. By adding this abstraction, we actually give ourselves the space to understand what it would mean to combine models, what it means to think about these combinations of models, much the way the relational algebra talks to you about combining tables, about the logical operations to be done there. But let's start out by spending a little bit more time on BQL and what you can do with that. So we're gonna look at some data. Satellites are cool. People like space. Who knows satellites? Anybody? One. Okay, cool. I'll make you answer questions later. So satellites. This is a public database off the internet. It has a bunch of satellites in it, and we're going to say, okay, I don't know anything about satellites, but I am funded partly by the Air Force Research Lab, and it's their job if the NGIS doesn't see it get launched, then it's their job to find out what the hell it is. And so here's a pretty reasonable question. If we have a satellite in geosynchronous orbit that we've never seen before, so it's not in our data, there's a satellite in geosynchronous orbit we've never seen before that has a dry mass of 500 kilograms. What's it probably for, and what countries might be operating it? All right, so let me switch to an actual demo-shaped demo. So this is a Python notebook. How many people know Python notebooks here? How many people in the back of the room can actually read that? Let me actually just do presentation mode, etc. All right, and I can take away that, and take away that. All right. Actually, this is a good question. How many people use Python notebooks every day? Okay, cool. So some of you should tell me afterwards. I want like 3 people to tell me something I'm not doing in a Python notebook that's cool and I should do it, because I'm sure I'm not using this tool to its full extent. All right, so we're in a Python notebook, which means that we got Python code in these sort of gray blocks. We got text. This is all stuff you can download, more or less. Actually, this is my modified version for presentation purposes. So we're able to load up BayesDB. BayesLite is distributed as a BayesLite's distributed open source. It's a you can pip install BayesLite, pip install BDB contrib. BayesLite is based on SQLite as a storage engine, so it's running on your single workstation. It's just allowing you to explore and query the models that have been loaded up. So I can load data. I can query the data using SQL. So, if I know the International Space Station exists, I can ask, to see what's here. And this data is useful. The reason we like to use it is it's got different kinds of information. It's got political factors, who's using it, what's it for, who paid for it. It's got physical things like apogee and perigee, and it's also got technological details like mass, power, stuff like that. So we got 1,200 samples, and that's actually interesting. Big data. I hate the word big data. We say big data because the only thing we know how to do with data is weigh it. We should actually be talking about the predictive power of our data. So we have 1,200 samples of data. We can actually start saying some interesting things with a certain level of confidence given 1,200 samples of data. We have all the GPS satellites, for example. We can do stuff. It's a Python notebook, so you can plot in it, etc. You can even get errors. All right, so we're going to query the implications using of our data. So suppose we got this unobserved satellite. How do I do that in SQL? How do I look in or what would I do if you have that question? Would we look in the data, we look for a similar satellite in the data? Yes, that's the answer to start with. Eventually you're going to use my tool, it'll be cool. So if we look for a satellite in our data that's similar, we find exactly one satellite. It's an Indian meteorology satellite. The gentleman in the back who knows satellites.
I don't know that one.
I know you don't know that one. Do you now believe that it's an Indian meteorology satellite?
That one is?
No, the new one is. The new one. The unknown
Not
one.
yet.
No. What would you do to fix it? How would you look more deeply?
Let's see. I probably want to know more about. I'm trying to read that actually.
Oh, I'm sorry. Yeah, I meant to ask if people read it in the back, which probably
Yeah,
they
you
did.
did. It's a little harder.
You didn't know I was going to make you fix it. It was a quiz. So one thing you might do is say well, maybe it's not exactly 500 kilograms.
Yeah,
That's pretty legit. Yeah. All right. So we'll say we got the between keyword. We can say between 400 and 600 kilograms. Look, they're both Indian. One's communications, one meteorology. Now do we think it's probably Indian because India likes launching 500 kilogram satellites? Questionable. So we can go bigger. And so we can say, let's say 300 to 700. Now I get 13, 14 different satellites from Malaysia to Norway. So this is interesting. So in order to answer a question from my data, what I did was to gradually ask a less specific question. Because I'm well, if I ask too specific a question, I get no useful answer out of anything. Because statistics can only tell me about generalizations over the whole of my data. And when I subset the data, I get bad answers and overfitting. And this is something I see a lot in data science. People say, in order to make my predictor less fragile, I'm going to put fewer columns into it. And that's weird, because if I had somebody who's an expert on satellites, I wouldn't ask them the least specific question in order to get the best answer. I'd actually just ask them the question. They'd know it was important, and they just tell me. So actually, to the extent you know satellites, satellite in geosynchronous orbit weighs 500 kilograms. What's it for?
I have a foggiest clue.
Really? What are most satellites in geosynchronous orbit for?
Communications.
Communications. Good answer. So we might say, okay, I'm bothered by this process, and Tibbetts is going too slow. So let's look at just the satellites that are in geosynchronous orbit. Okay, yeah. Now we get a histogram that's now I feel like I'm learning something. So now I feel like I can make a generalization from this because I've got enough data where I can say, okay, most satellites in geosynchronous orbit are for communications, and most communication satellites are from the US. Because we launch a lot of satellites, we really like television, who knows what. But so now we know about satellites in general in geosynchronous orbit, but we kind of had to throw away that information. So let's switch to BayesDB. Or rather, we were using BayesDB, we were just using the SQL part. Let's switch to using the BQL part. So the first thing we can do is build a model, train 32 models. So we have an ensemble of models from the default meta model. We're just saying ignore the name, it's not helpful. Guess the types of all the other columns, analyze for 4 minutes. And now we can do what we call simulations. So we can say simulate, and this is, I'm going to have to zoom out a little bit so I can get it all on the screen. So we can simulate from the posterior distribution of our model. So the model, in this case, it's an artifact of the current tool, is named satellite CC. So the model, the population is named satellite CC, and we say simulate given instead of select where. So given is the information we have, simulate says I want samples, and limit 1000 says I want 1000 samples. And I get this plot. So this is good, and it's in green to sort of help people remember that these are made up satellites. So what I just did is make up 1,000 satellites knowing only that they're in geosynchronous orbit. And it's cool because it actually sort of matches the distribution here. It's a little different. China and Russia and multinational kind of flipped. We go China, Russia, multinational instead of the other way. That's all right. So, now we are looking at geosynchronous satellites in general, and we've done our first simulate query. But let's get back to the question we actually had, which is what's this satellite for? So now we can ask the same kind of question. We can say, given the class of orbit is geosynchronous and the dry mass is 500 kilograms, now give me another 1,000 satellites. And this is like the key underlying capability, one of the key underlying capabilities, the most visceral, which is to say, the goal here is to be able to say, what would the model imply about the future? What would the model imply about things I haven't seen yet? What's the implication of the data? And what you see here is we went from, it did change. This, we have 27% USA communications, and here we have about 24.5%, something like that, USA communications. It changed a little bit. These are like all communications. And more of these are like meteorology and electronic surveillance. So what can we conclude from that? What did we learn about satellites? We learned that the mass of the satellite actually doesn't matter very much. That it's not an enormously useful piece of information, though it does have a small impact. How would we test that? How would we explore that? I'm done with the demo of this part of the demo, so this is legitimately a rhetorical question as opposed to I'm about to show you. How would we actually decide that model is believable?
You would start varying the mass and seeing if you still get the same type of pattern.
Right. Yeah. What else could I do?
Upper limit to the mass and see if some countries just fall out because they don't have the power to get something heavier than
That's good. Yeah.
300 kilograms.
Right. Remember, I've got other columns to play with too. Like I've got 24 different columns about this data.
But leave data out, you're going to cross-validate.
Cross-validate what? Cross-validate this conclusion?
How good the model is.
Yeah, okay. All right, you test the model quality. Yes, that's great. Okay. So one of the things I can do is say, well, what other things is it sensitive to? What else changes? Like, does it turn out that mass has more to do with age? Mass has more to do with when the satellite was launched or what battery technology it's using than it does with, and it turns out the US launched a lot of satellites a long time ago and they're super heavy. So what I can also do is think about what are the predictor relationships between my data? Which variables predict one another? That's not my math mode, it's someone else's, don't blame me. You can read that later. So this is a pairwise matrix that people sometimes, that people like to look at. We call this a dependence probability matrix. Where we're looking at pairs of variables. We have all the variables here, all the variables there, they're repeated. And so it's all ones in the diagonal because contractor predicts contractor, operator predicts operator. Sometimes people call this a correlation matrix. It's actually important to realize, how many people know what correlation is mathematically? Yes? Yes. Okay, people are there. All right. I'm talking to data scientists. So mathematically, I don't have a good way to check this, but mathematically, this is actually what the correlation in the data set looks like. Is anybody surprised that the correlation is sparse? Is correlation always sparse, usually sparse? Sometimes there? So correlation finds some relationships between things, but I want to draw your attention specifically to apogee and perigee. So here's apogee and perigee has a correlation of about 0.3. Person who knows about satellites. Are apogee and perigee correlated?
I don't know that much about satellites.
People who did better in high school physics. Are apogee and perigee correlated?
They're all ellipses.
They're all ellipses. And somebody famous and dead. Kepler, thank you. So what we have here is that when you look at these tools like ANOVA or correlation, when you look at these tools, they're not able to find more complex relationships. Whereas when we go back here, because of the structure of the default model, because of the way we're doing model building, we can actually find more complex relationships. And what we have here is not necessarily a statement about the strength of the relationship, but just the likelihood that there's some relationship. Because I ran my ensemble of models, and what I did is to survey my 32 models and say which of my models thinks these variables are related. So what I've effectively done, and this is where we come from probabilistic computing, what I've effectively done is model the power set of relationships between variables. And Alex is not allowed to gag when I say that, because that's probably not actually true. But what we're doing in a certain way, Alex is my math buddy in the room at the moment. What we're doing here is looking at the power set of relationships between the variables. And so what we do pull out is that contractor, country of operator, country of contractor all fit together. Those are really tightly coupled. And that's because Chinese companies buy satellites from Chinese manufacturers. There's another variable that's also tied together, longitudinal radians of geosynchronous orbit. Why is that actually? That's where a satellite in geosynchronous orbit is over the Earth. Why is that attached to those three variables?
People fly over their own territory.
Yeah, people launch geosynchronous satellites over their own territory or over territory that they want to pay a lot of attention to. Mostly over their own territory for television purposes. But then there's the rest of this. You actually get a nice tight block where apogee and perigee are coupled. Actually, all the physical constants and purposes of satellites, there's a relationship there. There's a strong relationship there between those aspects of things. There's a slightly weaker relationship between the power and the mass and stuff like that. We've been questioning whether we plot these correctly. So the way we draw these, we actually pull your attention to the dependencies. But sometimes actually the independencies are more valuable. Because the other thing this says is that actually country doesn't help me understand whether the satellite will be in geosynchronous orbit or what it will be for, or how much it will weigh, or where it will be launched, or anything else. Which intuitively makes some sense. And so it says if what you're trying to do is figure out what country a satellite's from, well, you could ask what country it's from, or you could ask who built it. But it's actually going to be tricky to really nail down the country that's operating a satellite unless you know the longitudinal radians of the geosynchronous orbit. All right, so that's that. Oh, right, I meant to talk about Kepler. So this is interesting because one of the takeaways here, oftentimes when I'm talking to people, I start bringing in examples where the executives on those earlier slides, other people I've talked to have ignored the results of data science. They've said that, I understand what the data science says, but I'm going to go with my gut because I don't trust it. And there's an interesting question, which is like, should people trust data science? So when someone says I'm going to ignore data science and just go with what I know to be true instead, are they being a Luddite? Who votes Luddite? Nobody votes Luddite. Yeah, okay, cool. So people people don't trust data science, and they're kind of right. So the way I ended up joining this lab was I was building safety critical systems, monitoring for fires in oil and gas wells. And they were based on, I was doing the plumbing, the real-time systems and Internet of Things stuff with StreamBase at Tibco. But the people who were responsible for the machine learning had to sell that to the people responsible for safety at these companies. And they were like, how do I trust this system? And the answer was they really didn't know how to trust the system. And they actually said to me, would you bet your car that this system will continue performing as expected for the next 12 months? Maybe like we're going to change what pumps are in the well, or we'll start upping the volume, or we'll adjust this, or we'll change that. There's lots of things that are going to change. Would you bet your car that the system would keep working? And I was kind of like, no. And they're like, yeah, there's like a bunch of guys in Oklahoma, and I'm more or less betting their lives that this system will keep working. And that's really interesting, because like, people know they should be making these decisions with data, but they don't have the tools that can get them to the confidence that they want. And our conceit is that the reason they don't have that confidence is because they're producing very fragile models that can only answer one question. And what they need is the ability to produce models that answer many questions, models where you can explore them, models where you can understand what's implied. And then in doing so, you can actually get to a feeling of confidence, in some ways similar to what you get with a human expert. Right. So, right. Oh, sorry, I forgot the joke line here instead of the guys in Oklahoma line. So if Kepler had been using Hadoop, then we wouldn't have the Enlightenment. Because this was actually the relationship that was strong enough and beautiful enough that it basically created the idea that physical laws are defined by simple equations. And that allowed Newton to develop calculus, and that allowed science to happen. And so when you just use these simple mathematical tricks to look for simple relationships, you can miss really important relationships. So this is what the satellites look like. And yeah, there isn't strictly speaking correlation there, but there's meaning there, there's structure to it. There's something you can find if you spend some time on it. And that's the trick for us, is how do we use computers to help you spend the time on it and understand what's implied. All right, how am I doing on time? I have a bunch of other cool stuff I could demo, but I want to make sure that I actually hit all the back-end modeling stuff. Yeah, I'll talk about country phenotyping, this stuff. Yeah, I'll come back to that, that's fun. All right, so modeling language. So we've got this model independent queries. People are like, who wants BQual now? People like this idea. They're like, no, get it away. It's going to take my job. Okay, so we need the back half is why it's not taking your job. Don't worry, the automatic modeler isn't that smart. Okay, so what are we doing for this automatic modeling? So people can ask an infinite number of questions. We need to create a baseline model so that they can ask questions even when it's not important. And then we need to create the ability to optimize those models. So right, correlation. So we could just do some big Mongo correlation type thing. What's the correlation in these data sets?
They're all the same.
They're all the same. And what is it? 0. Yeah, flat line.
Depends on which correlation coefficient.
Ooh, yeah, okay, what would we do to do better? Or would they all be kind of, I could pick different distributions and anything would fall apart.
There's actually a nice technology out of MIT called MINE, or mining correlations and standard.
Yes, but it's not Bayesian. We have a Bayesian version. We'll talk about that. Well, we won't talk about that, but that version sucks because it's got too many heuristics in it. Sorry, they're great. It's good, but there's, yeah, actually that's thank you. All right, so we could do something different. Let me show you what we're doing. So what we're doing is looking for mutually predictive subsets of the data. So this is the default meta model in BayesDB running on those kind of distributions, and what's the shape it's able to recover. And there's papers on this called, the underlying algorithm is called crosscat for cross-categorization. But what's really going on is we're looking for these mutually predictive subsets. So you're going to find these sort of chunks, they're going to be more or less square. You could imagine tuning meta models and having more and more sophisticated meta models that can find different shapes, that can find different kinds of relationships. The trick is, most of your data is not two-dimensional. Most of your data is actually quite complicated. If columns are dimensions, D, most of your data contains a lot of dimensions. So we need a probabilistic meta model for inferring model structure. That's cool. It reminds me of scheme, but maybe it doesn't remind the rest of you of scheme. So what are we going to do? What does it mean to infer model structure? So there's different ways the data could be mutually predictive. Given 3 columns and 4 records, I could be pulling, everything could be defining itself. Everything could be mutually related. Or it could turn out that I've got 2 groups of records, or 2 groups of columns and different groups of records within those columns. It could turn out that Descartes' daemon has structured my data and nothing means anything. But there's different structures that you could expect to find. The problem is there's a combinatorial explosion of possible categorizations. If all I have is 3 by 3, I get 205. 4 by 3, I get 4,000. It just keeps going up badly. So what are we going to do? What are we going to do? We are going to use probabilistic computing. We're going to use a semi-parametric Bayesian algorithm to identify the right assignments of records and columns into these clusters. And that's why we're going to run large ensembles of models, because different markup chains are going to find different local minima. And this is interesting because it's actually, at the bottom, based on some work. Our lab is actually affiliated with Brain and Cognitive Sciences at MIT and Josh Tannenbaum's work. At the bottom of this algorithm is actually an exploration of how humans make judgments about data. So I call this toddler crosscat. So this is a movie that just finished of the process of assigning animals and traits into these clusters, and which is something you could imagine actually sitting a toddler down and like making them do. And if you were Joss's grad student, that could be a thing you spent your time on. The important thing that's going on here, what comes out here then is you find these sort of nicer chunks of data where I've actually collected a whole bunch of mammals together. I've collected all the animals that live in the water together. And I've taken the lives in ocean column and put it there. I've got flying and to some extent tree-living animals there. So I've been able to find these mutually predictive things and run the model forward until I find places and assignments for things where it's easy to build a model inside each little cluster. And so that's where the hierarchy comes in. So that allows us to figure out what's going to be important to draw a predictive relationship between one thing and another. Questions on that? It's pretty cool. Yes, Connor.
How ragingly computationally expensive is this part of the process?
In like 4 minutes, we can run the satellites data on 32 models. So there you go.
Okay, so 1,000 rows in your satellite?
Yeah, it's like 1,000 rows. So it's, oh, sorry, how ragingly computationally expensive is this? That's an awesome question. Let me back up and give you the higher level answer. So probabilistic computing is about 10 years old. Vikash Mansinga, who runs the lab, was involved in foundations there. And there's really two technologies right now that are being quite successful. How many people are using Stan? How many people think Stan is cool? Oh, Stan's cool. But what's going on here is, it turns out these things don't have to be ragingly expensive. But most of the research done in probabilistic computing is done by statisticians, and statisticians don't really know what big O notation is, never mind what compiler optimization is. So we can make this, roughly speaking, linear in the volume of the data, and we can actually make it distributed across multiple machines if you want us to. So that's linear for each transition of the markup chain. So then the question is, how many chain transitions do I have to run to get to a good model? Which then leads to the question of, well, what constitutes a good model? So there's an interesting question about how to measure model quality in these, and if you want to work on that question, you can get a PhD. But it turns out that with some pretty good heuristics around model quality, we can very quickly converge these towards the kind of predictive models that are being successful right now. And so the answer is, we can run these on what I call medium data. And if the data fits on one machine, we're good to go. Data spread across multiple machines, we should back up and talk about what we're going to be doing. And if people want to do more of that, we should talk about it. Because it's possible to spread this algorithm across multiple machines, but what we found so far is that most of the predictor relationships that are important can be found much more quickly than that. Other questions? Beauty. All right, so yeah, I've got one of these. Oh, I jumped ahead. So what can an automatic model tell you? It can tell you that dependence probability and get you Kepler's laws. There's also some interesting questions, which are, what can I do if I want to refine the model? So I can actually, goal is to allow domain experts to get involved here. So I can actually make statements about causal relationships in my data or dependencies. I can suggest or put or assert them. I can also say, hey, I know the answer. Either I have a really cool machine learning model, or I have an analytic model, or somebody told me how this stuff works. And so I can refine the model by actually creating a compositional model. I can say, for some of my variables, use this random forest. For some of my variables, use this plug-in model, Kepler's laws. For some of my variables, stick with the default meta model. And these are all below what we call the GPM abstraction, the generative population model. So what we need is just simulate log PDF, and there's some other bits that help us optimize it. But simulate and log PDF is enough to get your model under equal. So what does that mean? So this actually ends up being very interesting, because since I have this ability to ask questions in a structured way, I can actually run multiple models, I can try out different models, I can have domain experts explore those models, I can have domain experts compare those models. So what I have here is 3 different centuries of data on the same graph. So I have the empirical observations, the blue data. So the blue data points are the actual satellites. The green data points are the sort of data science, the red data points, pardon me. The blue data points are the empirical observations. The red data points are the baseline model, the model that's uninformed by actually knowing Kepler's laws. And then the green data points are what happens when we say we're going to constrain some of these columns according to Kepler's laws. And what you get is an improvement in predictive accuracy. You can see that a little bit better on this plot, where the purple line is where they should be if you didn't screw up Kepler's laws. And you can see that a lot of our default meta model simulations are off the line, because the default meta model doesn't really know calculus. It's just kind of approximating it. So that is kind of what we've got. We've got this BQual language that gives you a bunch of new query abstraction capabilities. We've got the underlying modeling technology that lets you get started quickly. And we've got the compositional modeling, which says once you've gotten started quickly and figure out what the important questions are, how do you actually get better answers to those questions? So, what else can you do? We're actually pretty good on time, so I'm going to talk about 2 more cool things. Let's do this. So one thing we can do is talk about, having modeled the data, we can start to talk about the mutual information between different bits of data. So this is a project we've been doing with the Gates Foundation. And if I was able to switch windows a little bit better. There we go. No? Where's my thing? There it is. So this is about, there's two things we're doing here with Gates. One is helping people understand things about countries. So everybody knows intellectually that Africa is not a big monolithic continent where everything is all the same. We all know that, sort of. Sometimes we forget. But when the Gates Foundation actually organizes delivery of aid, when they think about running analysis, when they think about assigning people jobs, they actually tend to still assign them geographically. Even though actually basically everybody sits in Seattle, except when they're sitting in like Australia or Toronto or who knows where. So what we're doing here is two things. We're helping people understand how countries relate to one another. So what we've done here is to say Kenya or China. Let's look at attributes related to water quality and look for similarity. Where, if I knew something about China and water quality, or if I knew something about China and the education of women, what other countries do I know things about? Where is it similar? Where is it being brought together in modeling? Where do I have that notion of mutual information? And the reason I like to present this is to help people understand, it's not just about being in a Python notebook and being able to issue queries and copy paste them. It's actually that once you get this thing fast enough, to Connor's point, and actually the important thing there is, so you were asked about how fast the modeling is, but the querying is super fast. So we do all the work ahead of time. And so all the questions that you can ask are able to run quite quickly and able to allow you to do that sort of inspection, exploration type interaction. And this is a big chunk of what's coming next for us, is how do we think about the right way to visualize this stuff? Because there's new things we can do that people haven't seen before and new ways to help people understand them. One of those is my current prototype. Is this idea of a contextualized analysis. So this is looking at a data set from Harvard about economic mobility, intergenerational economic mobility. And there's a lot here, and you've never seen this kind of a plot before, so I'm gonna slow down. So the big blue line is the observation for Colby, Kansas. It's 0.13. The histogram that's biased towards the right, the green and blue one, the blue lines in the histogram are the actual empirical observations. And the green lines are a general simulation. Where does the model fit those observations? The red is really interesting. The red is saying, if I contextualize the simulation to everything I know about Colby, Kansas, what would I expect the outcome to be? What would I expect the value to be? And so what we can say is that Colby is 0th percentile observed. Anybody from Colby, Kansas? No, okay. And 3rd percentile in context. So given what we know about Colby, we actually pretty much expect them, well, we expect them to be down below. We don't expect them to be quite that low. We have the same plot over here for Huron, South Dakota, which is at 53rd percentile observed, but 100th percentile given what we know about them. So given what we know about them, we'd expect them to be actually somewhat similar to Colby, but actually they're doing really well, assuming you like economic mobility. So what's the conclusion to draw from this? What have I learned about Huron, South Dakota? What's that?
There's a lot of economic opportunity.
No, it doesn't. It has about a median amount of economic opportunity. Well, maybe. I don't know. That's a good question.
They're doing something right.
They might be doing something right. They're doing something I'm not observing. It might be being awesome in some abstract way. It may be that there's some rich guy who sends everybody to college like for free. I literally don't know. It might be that my model's bad, actually. But what I do know is that there's something that my model doesn't predict that's going on in Huron, South Dakota, which means it's probably worth paying attention to and saying, is there additional stuff that I can observe? It's also potentially, I could say, what are the components of that? So I can look at one place, I can look at Harrisburg, Illinois, and say, okay, well, what if I contextualize, instead of contextualizing it on everything I know about the county, I can contextualize it on the Gini 99%, which is the bottom 99% of people, what's their economic inequality. And if I condition on that, then I see that I would expect Harrisburg, Illinois to be doing better than it is. Okay. Well, I could run this a different way. So I've got this BayesDB thing. It can actually tell me which variables are going to matter. That's not on my slide, but I can actually give you a rank ordered list of variables that are going to help you predict the absolute mobility for women in Harrisburg, Illinois. And what that would tell you, actually, if I flip over to a notebook, am I going to get away with doing that? If I flip over to a notebook and say equal opportunity, so I can run a query like estimate the dependence probability with AM females from the columns. This is like that heat map thing, but I'm just going to get one list. And it tells me that the most useful columns here are a bunch of other columns with absolute mobility. Okay, that's not helpful. But then it tells me the ones that start getting interesting are that the fraction of adults divorced, the fraction that are religious, have a strong probability of helping determine economic mobility. Okay, let me go back to my novel chart. So what my novel chart says is if I condition on the fraction of adults who are divorced and the fraction who are religious, then I get a distribution that actually is kind of where I'm in the middle of it again, sort of. So if all I know is that the fraction of the adults are divorced and the fraction of the adults that are religious, then I'd expect outcomes of Harrisburg, Illinois, they're about the same. So what does that tell me? If I wanted to fix Harrisburg, Illinois, what would I do? Tell people to be less religious?
Or you don't know which way.
Yeah, we don't know which way. That's good.
Or more divorce.
Or more divorced. Yeah. Single mothers have more mobile daughters. Who knows? I have no idea. I literally actually don't know the answer to what we should do. And I know almost nothing about Harrisburg, Illinois. I'm just a data person. But it's actually also worth noting that, while the simulation now tracks the general simulation pretty closely. So another thing you could say is that Harrisburg, Illinois isn't actually special in the number of the adults who are divorced or the fraction that are religious. That all I did was to say, oh, now it looks the way I would expect it to look. But I didn't actually tighten the distribution, because the red distribution still has the same tails. So those actually aren't necessarily the variables that are predictive. We actually need to explore further and understand more and ask more questions to get a sense of like what would my model say is the reason or the potential reason for Harrisburg, Illinois to be at this point or a different point in the chart.
But there were other variables in the same correlation range.
And there are a bunch more variables in the same range. There's a bunch more things that I can ask. Unfortunately, I stopped preparing slides and got on the cheat. So that's where we're at. But there's more you can imagine asking. And that's the key thing I want to leave people with, in some ways, is that you should be thinking about what are all the questions I should be asking? Because science, if you get back to people should go read Feynman's original Cargo Cult Science talk at Caltech. Because it's really about the idea that science is about skepticism and about asking questions and probing why might we have gotten this wrong, and not being satisfied until you've asked all the questions that could explain why you got it wrong. And data science today has a bias towards finding the best predictor for this variable that nails the KPI and then using it to place ads. And if we're going to actually understand data, then we need to give people the ability to ask lots of questions, which means we need to start thinking skeptically and thinking about lots of questions. So BayesDB, you should download, you should install it, you should play with it. Machine-assisted modeling as a service is not actually up for general consumption yet, but if you're interested in modeling data, well, actually I got the next thing. Yeah. So you should download it and try it out. You should sign up for the alpha. And in particular, you should bring me data that I can publish, that I can model and publish, that we can use to understand where is our model doing a good job, where is our model doing a not a good job, and that we can get out there in the wild. And, since some of you are from Fidelity, if you have data you don't want to publish, then you should also talk to me, because we can do that too. Thanks very much, and I'm happy to answer any other questions. Oh, actually, I forgot another part of the shameless plug. If you want to work on this, you should also talk to me. So yeah, questions back. Yes, lovely.
During the training phase, does the system reserve some of the known training data and evaluate itself
No,
at the end? Why?
because it's Bayesian.
Shouldn't you?
I don't know, should it?
Shouldn't you? I'm just.
Yeah, I'm asking actually.
If you don't.
Yeah, so we don't cross-validate. Yeah, what? Well, what would we cross-validate on? Here's a different way to say it. So because we're not trying to nail one KPI. Like we don't have one question we're trying to get the best answer to. So if we reserve the data, how would we use it to validate?
You could punch out some known data.
Right.
Then run it through the simulation and see if it fills in.
Run the simulation and see if it happens to hit that data?
Yeah.
Yes, okay. Yes, and that is a very good, that's good insight. The right way to actually do model quality on this gets actually quite complicated. But, well, actually, I guess, yeah. Do you want to say why we don't hold back data, Alex?
Well, I think it really comes down to the fact that you can't do that very effectively unless you have specific questions that you want to answer. And so then once you've got a model and your model is giving answers to questions that you're interested in, then you can go back and do the kind of cross-validation that you're talking about, where you leave some data out and train and then test the answers that you're getting that way.
Cool. Others? Yes.
What do you mean by Python 2 on your slides? Are you using Python 2 versus 3?
Yes.
Okay.
We're academics, we apologize.
Okay.
It should be Python 3 soon. If someone wants to send a pull request to get it all to be Python 3, we will consider it.
Sorry, what, can you repeat the question?
Oh, the question was, are you using Python 2? And the answer is yes. For parts of it are Python 3. Anyway, go ahead.
Can you talk about where priors come into this? Can you model those in the...
Yeah. So the prior is, to some extent, this, which I blew past. Well, it's different. There's priors on two things. There's priors on the simulation, which are the given parameters. And there's priors on the meta model, which are the kilometer dependencies. So if you have an expert who tells you that mass has nothing, I ran a salary survey, and it concluded that geographic location had nothing to do with salary. It concluded that because it was a salary survey of advertising executives, and they all live in New York, LA, and San Francisco, except for the ones who don't. And there was enough who did that the answer was, it doesn't seem to matter. Maybe we could do better with that, but an easy fix and an easy example that shows up in the paper is you can actually just assert that state does matter, and then the system will take that into account. So this is part of where you're setting the priors. In some way, the prior for BayesDB is that everything is coupled to everything else, and then we look for the places where we can decouple things. And so what you're doing here with these assertions is sort of making some couplings more sticky. Other questions? Or someone over there?
So you have, I haven't had a chance, this looks awesome, I haven't had a chance to play with it, but you've got, is it SQL-like version of this?
Yeah, so the underlying database, this is all wrapped around SQL-lite.
Which means you can do traditional relational queries.
Yep.
Like this. Any plans to roll it out to other?
The underlying database is sort of two questions. The underlying database kind of doesn't matter. Alternatively, if you wanted a better database than SQL-lite, we actually there's a bunch of different trade-offs you'd make. So when we think about the single workstation version, it's likely to stay in SQL-lite. There was an early version that was based on Postgres, and that just turned into a headache. So SQL-lite was a good simplification there. It also gives us these nice single-file databases we can sling around in version and stuff like that. When you think about scaling the thing up and realizing that you need a database that can handle more than a terabyte of data, there's a bunch of other trade-offs you're going to make, and the system becomes a systems engineering problem. And so it's still going to be the case that Postgres and Oracle aren't right. Yes, in the back.
You mentioned actually trying to answer questions with some confidence.
Yes.
And you also talked a lot about the simulation capability. Through the simulation capability, are you able to also report back columns of confidence intervals?
Yes, yeah. So we can certainly give you confidence intervals. These violin plots pop up there. So this is when I skip past where I'm inferring. So I can infer missing data. I can also infer explicit, and I just say, give me the data, give me the inference even if you have data. And I can also, instead of setting a confidence threshold, I can actually pull out the confidence as a number so that I see the confidence as data and then I can plot it. And what you conclude here is that my model is making more confident assertions about low Earth orbit satellites when it comes to inferring their orbit type than it is about elliptical orbits when it's inferring their orbit type. Because even though we relatively often think it's unsynchronous, there's a bigger spectrum of confidence. Yes?
Does it work with multiple tables and hierarchical data?
Good question. There's a notion of population design, which is almost but not quite entirely unlike data normalization. And what you actually have to do is think about what questions you're going to want to ask and design your population structures to match the questions instead of thinking about it as normal SQL table joins. You can imagine running this against multiple tables, but then you end up with a very large number of new join types, and we're still exploring the merits of that. Where we are right now is mostly you want to put the data into the population structure that's going to make sense for the simulations, the queries. So for example, if you're modeling senators and campaign contributions, you could have a table of senators with 100 records in it, and the campaign contribution data is out there. Or you could say, actually, I want a table of votes. Because what you actually want to think about is, what do I want to be able to simulate? I don't necessarily want to simulate novel senators, I actually want to simulate votes. Or maybe sometimes I want to simulate senators. So oftentimes the same underlying data actually inspires multiple population designs. And those population designs can involve some denormalization or joining of the data. Others? Awesome. Good crowd. Thank you very much.